In this lesson, we're going to look at energy resources. The first aim is describe the factors we use to evaluate the effectiveness of using different energy resources, then explain how different energy resources are used to generate power, and then explain examples of energy changes that we would link to each energy resource. I will deal with these two aims simultaneously. You'll see why later. So when I was a kid, sci-fi Hollywood blockbusters were generally about things like dinosaurs and robots, perhaps aliens and superheroes. Now obviously that hasn't changed, we still have those, but there's a new contender. In the last 10-15 years we've seen the emergence of disaster movies. Take films like 2012 or The Day After Tomorrow. You see, I never would have figured a film about the environment would have made the Hollywood blockbuster scene. Now those are fairly obvious examples, but also they're more subtle examples. For example, in The Matrix, human species are referred to as a virus, in that we have an inability to live harmoniously with our environment. We use, exploit, and destroy. Even the other day I was watching a film called Kingsman. In that, Samuel L. Jackson plays a villain, a supervillain, who once again describes the human race as a virus. A species is doing irreversible damage to our planet. It does raise the question, why is our environment getting so much limelight? Well, ever since the late 1800s, we've been burning fossil fuels like crazy. These release harmful gases into our atmosphere, and now we are really beginning to feel the impact of that. The problem is, too many people treat these issues like films, in other words, like fantasy. But if we don't find solutions very, very quickly, we are going to do irreversible damage to our planet, and this will have a serious impact on our species. So, what is an energy resource? An energy resource is a form of energy we can use to generate electrical power. These can be broadly split into two groups, non-renewable and renewable energy resources. The four non-renewable energy resources you need to know are coal, oil, natural gas. These are all fossil fuels because they are in fact the fossilized remains of once living things. Coal being from trees and oil and natural gas being from plankton and other forms of aquatic sea life. Nuclear power, for which we extract the metal uranium as a fuel source, is also regarded as non-renewable. What this means is they will run out someday. In other words, the rate at which we're using them is so rapid compared to how slowly they form, for all practical purposes they will run out. Extracting such resources damages the environment, and when we burn such resources we also release harmful gases which damage our environment. However, currently non-renewable energy resources provide most of our world's energy. But as you can see, there are plenty of alternatives. These are the renewable energy resources. We have hydroelectricity, wave power, tidal power, wind power, solar power, geothermal energy and biomass, all of which we'll look at in more detail in a bit. These will not run out, they are less damaging to the environment, but they are less reliable, a lot of them depend on weather, and they provide less energy. So really this lesson is about weighing up the pros and cons for these two groups of energy resources. But how do we get electricity from such resources? Well, I'll quickly show you how we get them from non-renewable energy resources, in other words, the main way we get them. A coal, oil or gas power station have three main components to them. You have a boiler where you burn the energy resource creating heat. This heat will then heat up water in a pipe which will turn to steam. Then you have a turbine chamber. When water turns to steam, it expands significantly. This causes it to leave the pipe under very high pressure, enough pressure to turn a giant metal fan we call a turbine. Now, if you've seen the tutorial on generating electricity, you'll know that a turbine can be used to drive a generator to produce electricity. In this case, we've just got a wire coil rotating around and round in between two magnetic fields. Nuclear power is very similar, except for we do not use a boiler, we use a nuclear reactor. Here we have uranium fuel rods as the energy resource, and they will be used to heat up a liquid called a coolant. This is achieved through a process called nuclear fission, but you'll learn more about that in P2. That coolant then heats the water which is running through pipes, and once again the steam drives a turbine and the turbine drives the generator to produce an alternating current, i.e. electricity. So now we're going to look at how to evaluate energy resources. This is very likely to be the basis of a number of 6-marker questions. And as you can see, there's an intimidating amount of information to get through. But luckily, a lot of this is just common sense. So let's start here. The first factor we consider are setup costs. Quite simply, larger power stations cost more, and this may surprise you, but renewable power stations generally have to be larger for the same amount of energy output as a power station that uses a non-renewable energy resource. Other things to consider are resources such as hydroelectricity and nuclear power have high engineering costs because there's risk involved, so we must make sure they're safe. So I'm going to add these results to this evaluation table so it gives you a good overview at the end. So in terms of setup costs, coal, oil, gas and solar power have relatively low setup costs, whereas most renewable in green here have high setup costs as well as nuclear. So now let's look at this section. We must also consider how long it actually takes to set up the power station. Most energy demands are fairly immediate. If it takes years, it might not be a viable option. So once again, as you might imagine, it's affected by the size of the power station. It's also affected by the complexity of the parts involved in making that power station work. And also certain things require a lot of planning permission, especially nuclear power. So when we consider setup time, we get a similar but slightly different story. Gas is one of the easiest things to set up, so we give it a big green tick there, and solar power is also very quick to set up. The rest, due to planning permission and complexity, take significantly longer. These are sort of in the middle. So now let's look over here. Quite a simple point really, it's about running cost. Renewable energy resources have much lower running costs because there's no fuel to burn. For example, you don't need to pay for the sun or the wind. So when we consider fuel cost, we get almost a negative image. All the renewable energy resources get a green tick. Biomass is very cheap, it's just animal waste and crops, but you still have to invest a bit of money into growing crops. Renewable energy resources are significantly more expensive when you consider fuel cost. So now let's look at reliability. Well, non-renewable energy resources are very reliable until they run out, that is. Whereas renewable energy resources can be very dependent on weather, such as wind power and solar power. Exceptions to this are geothermal, tidal and biomass. I'll explain what these are in a bit. So here you can see that all non-renewable energy resources are more reliable, and biomass and tidal power and geothermal power from the renewable section, and that's because biomass is essentially burning crops and manure, that's everywhere. Tidal depends on the moon and the sun, and they're not going anywhere anytime soon. And geothermal energy is based on the heat from the mantle, and our Earth's mantle isn't going anywhere anytime soon either. So now let's look at location. The key point here, and it's very logical, resource availability affects the location of a power plant. For example, if you want to use oil-fired power, then it needs to be near the coast due to transport issues. For obvious reason, wave power and wind power stations also need to be located near the coast. Hydroelectric power stations need to be somewhere where it's hilly because they need to allow water to run down a hill. Also, you need somewhere which is wet or has rain frequently so you can store the water. Coal power stations need to be near mines. Nuclear power stations need to be well away from human populations. Whereas geothermal energy relies on plate tectonics moving hot rocks closer to the Earth's surface, and that doesn't happen everywhere. So you're looking for regions with volcanic springs, such as Iceland. And tidal power needs to be located on river estuaries. There are some which are not restricted geographically speaking, such as solar power. Luckily the sun shines down on us all. Biomass, because crops pretty much grow everywhere. And gas is quite easy to transport because we can use pipes, so it can be transported long distances. So our table now reflects this. In terms of being geographically unrestricted, we have to give a tick for gas, biomass and solar power. Coal can be transported with relative ease, but it's still preferable to be near the mine, whereas the others are significantly more restricted where they can be located. Okay, last but certainly not least, the environmental impact. In my opinion, this is probably the most important thing to consider in terms of where we are with our planet right now. Non-renewable energy resources, while burning them, create atmospheric pollution such as sulfur dioxide, which causes acid rain, carbon dioxide, which can lead to the greenhouse effect. Also with non-renewable energy resources, we are causing damage to our landscape when we extract the resource. This can destroy habitats. We're also using up a limited resource, which is never a good thing. Some renewable energy resources can also cause damage to habitats when they're being built, such as hydroelectric and tidal. So now I'm just going to go up here for a sec. Renewable energy resources have issues as well. If they're weather dependent, they must be exposed, which can cause visual pollution. For example, many people complain about wind farms being an eyesore. Although rare, some power stations can cause catastrophes, such as nuclear power stations when they have a meltdown or when a dam bursts in a hydroelectric power station. And finally, and perhaps less significantly, noise pollution. The following types of power stations are very noisy: coal, oil, gas, nuclear, wind, and biomass. So I've pigeonholed these ones quite crudely, but there is some justification here. In my opinion, those which release harmful gases into our environment are the most damaging. Nuclear power is pretty great on many levels, but when it goes bad, it goes very bad. But as these events are pretty infrequent, and nuclear power doesn't release any harmful greenhouse gases, I've given it a neutral rating, though disposing of nuclear waste can be an issue. Biomass I've also given a neutral because it requires a lot of land to grow the crops. And if we don't grow enough crops, then the carbon dioxide they release when burnt will not match the level of carbon dioxide taken in through photosynthesis, so they're not always carbon neutral. All the others largely are concerned with visual and noise pollution, which aren't as great a deal as atmospheric pollution. Again, hydroelectric, because it can cause catastrophes, I've given it a neutral rating. So there you have our evaluation table. One thing's clear, there's no perfect solution here. But if we don't start making the shift from here to here, then we're going to be in trouble. My tip to you is remember these 6 factors here, remember the different types of power, and see just by using this table alone if you can just talk through some of these and give reasons for why there's a tick there and why there's a cross there. Remember, in a 6 marker, it'll probably ask you compare one power station with another power station. You won't know which ones, but it's very fair to assume that one of them will be from the non-renewable category and the other one will be from the renewable category. And also, you don't have to discuss every single factor, 2 or 3 will be fine. So that's how we describe the factors we use to evaluate the effectiveness of using an energy resource. So we've already looked at how non-renewable energy resources generate electricity, but now let's look at renewable ones. I like this bit because it always reminds me of that board game Mousetrap, where you have one knock-on effect leading to another. So with hydroelectric power, for example, such as the Hoover Dam in Arizona, you have a barrier, the dam, which basically blocks or traps rainwater at a height on a hill. When the dam is raised, the water is allowed to run through the dam down a hill. When this water runs through, it drives the turbine, which drives a generator, which produces electricity. Now, you can't build something like this without damaging the environment or potentially destroying habitat. Even when you flood the lower valley, you can destroy habitat. But one huge advantage of hydroelectric power, providing you have the water and storage, you can change the amount of energy output by controlling how much water is allowed through. And also, I do realise that I've put a cross on the table for reliability. And that's because hydroelectric power depends on whether there's enough rainwater available. But if there is, it's an incredibly reliable energy resource. It really depends on where it's located. In terms of energy, we basically tap into the gravitational potential energy the water has high up on a hill. As the water runs downhill, the gravitational potential energy in the water is transferred to kinetic energy as it moves. The kinetic energy in the water is then transferred to the kinetic energy in the turbine as it turns. Then the turbine drives the generator to convert that kinetic energy into electrical energy. This is what I mean by describing energy changes, and you do need to know this for the exam. This one's particularly popular. Next we have wave power. Wave power is useful for, let's say, generating electricity if you live on a small island. Basically, waves move up and down. You can use waves to force air through a pipe, which then turns a turbine, which then drives the generator to produce electricity. Currently, most wave farms are located near coasts where the waves are generally smaller, but we're finding ways to tap into the energy in larger waves by building more wave farms offshore. The biggest problem with wave power is it's not incredibly reliable. Location is a big issue here. So the energy transfer here is the kinetic energy in the waves is transferred to the air in the pipe, which in turn is transferred to the kinetic energy in the turbine, which is transferred to electrical energy as the generator does its thing. Notice how I'm using the words energy in my language. It's a difficult word to use correctly. Hopefully through repetition you'll pick up on it. I want you to avoid saying things like the kinetic energy in the turbine is transformed into electrical energy. Technically that's incorrect. Energy doesn't transform, it gets transferred. What I mean by that is energy is always energy. Think of energy as the passenger and the form as different vehicles that transport that energy. So the kinetic energy in the waves is transferred to the kinetic energy in the turbine, which is transferred to electrical energy as the generator operates. Tidal barrages are an interesting one. They require a river estuary, that's where they're located. A river estuary is a semi-closed section of water which has a few streams running into it and it has an opening to the sea. This is how it works. Basically, like before, like hydroelectric, you have a dam separating two sections of water. As the moon rises, the gravity pulls the tides up, and changes in night and day cause the tides to go up and down and so on. When the tides are up, we can hold that water back. You can see now the water has a store of gravitational potential energy we can tap into. So beneath the dam are a series of turbines which, as the water flows through, turn the turbines which drives the generator which produces electricity, like so. So here the gravitational potential energy in the water is transferred to kinetic energy in the turbine as the water moves through the dam, which is transferred to electrical energy by the generator. Tidal energy is very reliable because it relies on the sun and the moon's gravitational energy to tug on that water. And just like the hydroelectric dam, you can control the amount of water flowing through and therefore control energy output. But it is severely restricted by location. You certainly can't set these up anywhere. Wind power's the next one. Many people complain that they're a source of visual pollution, though personally I don't think they look that bad. This is probably the simplest chain of events you need to remember. Wind drives the turbine, which drives the generator, which produces electricity. Each turbine is fitted with its own generator, which means there's less sort of steps involved, less opportunities for energy loss. So it can be quite an efficient way to produce electrical power. The biggest issues are, as I said, visually noisy, also noisy, and you are really dependent on whether there's a strong wind or not. You might be in trouble if you need to supply more energy than usual. So here we have kinetic energy in the wind, which drives the turbine, which drives the generator to produce electricity. Solar energy is potentially wonderful, it's just very small scale. Light energy from the sun is captured by solar panels, which then produce electrical power. Solar panels work on an individual house basis. They're really good in certain regions where other energy resources aren't an option, but sunlight is readily available. If you're a country which is exposed to a lot of sunlight, it's an incredibly reliable source of energy. But even in cloudy regions like Britain, you can get enough solar energy to power the panel. But obviously this isn't perfect because you can't apply it at night time. So here the energy changes are as follows. Light energy from the sun is transferred to electrical energy by the solar panel. This electrical energy then can power any domestic appliance. Essentially, it's just a big battery producing direct current, unlike all the others which produce alternating current. A solar cell produces direct current. Geothermal energy really shows off how innovative we are as a species. This here is the Blue Lagoon in Iceland. I've had the pleasure of actually going and swimming in it. It's naturally heated by hot rocks near the surface of the Earth. You see, Iceland's a volcanic island. It just sprung up from the oceans one day, so it experiences much tectonic activity. So the people of Iceland really do make use of what they've got. Geothermal energy works as follows. A pipe is constructed which travels underground then back up again. Cold water is poured down the pipe. Now, due to the Earth's mantle, certain rocks have been heated up, and as the water passes over these hot rocks, it starts to boil and turn to steam. That steam drives the turbine, which drives the generator, which produces electricity. It has to be said that this is probably one of the best ways of generating electricity out there, next to no environmental impact, and the energy is essentially free. Granted, there are high setup costs, but the biggest issue is obviously geography. Unfortunately, at the moment, we can't just build these anywhere, but there's enough heat in the mantle for us to utilise the world over. So if you want to get rich, students, and save the world while you're doing it, make geothermal energy happen everywhere. So the energy changes here are: heat energy in the rocks is transferred to the water, as you can see here. The water turns to steam, which is transferred to kinetic energy in the turbine, which drives the generator to produce electrical energy. Last but not least is biomass. Biomass refers to matter from any living organism that can be used as a fuel. For example, farm waste, manure, landfill rubbish, plants, biogas, bioethanol. The great thing about biomass is it's potentially carbon neutral. For example, when you're growing crops, they take in carbon dioxide. When you burn them, they release it again, but they offset each other, so overall there's no net release of carbon dioxide into the atmosphere. But to make this work, we need a lot of land to grow enough crops to take in enough carbon dioxide. So this can be a problem because we also need land for food, and we have a growing population, remember. A biomass power station works just like a coal, gas or oil power station. Heat the fuel to heat up water, which turns to steam, which drives the turbine, which drives the generator to produce electricity. So this all starts off with chemical potential energy stored in the plants. As we burn it, the chemical energy in the plants is transferred to heat energy. This is transferred to heat in the water, which turns to steam. The kinetic energy in the steam is transferred to kinetic energy in the turbine, which drives the generator to produce electrical energy. So that's how we explain how different energy resources are used to generate power, and we've also explained examples of energy changes.